Today we're going to start with rotational kinematics. We're going to look at a lot of things that we've seen before, but from the point of view of a rotating reference frame. So, a lot of rotating systems are important. Merry-go-rounds and wrenches and figure skaters in the solar system. Let's start with a simple example here. We have a rigid body, so just like this looks like an egg, and it's rotating around this axis here. It looks like the z-axis in this case. And we're going to pick a reference line. So let's just look at it top down. We're going to do this two-dimensional for now. So here's top down. And the reference line here, if it's at this location, then we measure its angle with respect to the x-axis. So the angle of this body is just the reference line for the body measured with respect to the x-axis. And so we call it the angular position. And the angular position, can be measured in radians or degrees or other units. And if I want to find the distance here of a point that the reference line has traveled from here to here, s, that's related to the angle via the radius r, right? So there's this relationship that you've seen before between the angular position, the radius, and the arc length. So just as a simple example here, let's say I have something with I have a point here, and this is at a radius of 2 meters, and it's at an angle here of 30 degrees. Okay, so we can find this distance here that it's traveled from the x-axis. If this is the x and the y-axis, this distance here will be r times theta. Now, to use this equation to find the distance s has traveled in that arc length, we need to convert theta from degrees to radians. So we can use 30 degrees, and we can multiply times 2 pi over 360 to get our angle, and it's about 0.5236 radians. So if I plug that into this equation here for s in radians, so it'll be 2 meters times the radians, 0.5236 radians, right? We'll get that distance, and that works out to about approximately 1.05 meters. Different ways of looking at all this. One complete revolution, so all the way around once, is one revolution. That's equal to 360 degrees and 2 pi radians. So if I have something like here, 45 degrees, and I want to write it in the other units, I have to do the conversion, right? So 45 degrees, if I want to convert it to radians, I could do 2 pi over 180 degrees. That would be 2 pi radians over 180 degrees, and you'll see the degrees cancel out, and we're left with radians. And so my radians, 45 degrees in radians, 7,854 radians. I could also, if I wanted to, write this whole thing in revolutions. So once all the way around. So I could say 45 degrees, and the conversion factor here is 1 revolution is equal to 360 degrees. So once again, the degrees cancel out, and we're left with revolutions, and when we simplify down, we end up with 1/8 of a revolution. So it makes it 45 degrees is 1/8 of the way around. We're going to need to consider changes in angles. So if we have a rubber ducky here with an initial angle θ1, and then it turns to a different angle, the difference between those two angles is going to be our change in angular position. And this is an important sort of standard way of choosing a sign for the change in angles. Turns out a change counterclockwise is going to be positive, and a change clockwise is going to be negative. All right, so just keep in mind that counterclockwise changes in angle are positive, and clockwise changes are negative. That's the way it comes out. So let's just do a simple example here. We have a disk, and we have 2 bugs on a disk, okay, and the disk rotates 30 degrees. What is the distance traveled by each bug? So let's do it for this bug here first. Okay, so what is the distance traveled? So it's asking here, what is the distance traveled here, s, right? So the distance traveled is going to be, according to this equation in the top left corner, right? The distance traveled is going to be r times theta. So it's going to be the radius, which is 20 centimeters, times theta, which we have it as 30 degrees. But so let me make a note here. Theta is 30 degrees, but that works out to, when we did the conversion before, it works out to about 0.5236 radians. When you're converting to arc length like this, you need to convert theta to radians. So this would be times 0.5236. And what do we get for our final S? We get that it traveled about 10.5 centimeters, roughly. Okay, so when it rotated 30 degrees, this bug traveled a little over 10 centimeters. The other bug is going to travel the same angle, but the distance will be smaller, right? Because it's closer to the rim, so it's not going to travel as far. So the change in angle in this case is 30 degrees again, which is the same as 0.5236 radians. And in this case, instead of 20 centimeters, r is 10 centimeters. So when we do calculate S this time, because it's closer in, it's not going to travel as far, and that works out to about 5.24 centimeters. So it travels about half the distance. Next, we start thinking about angular velocity, right? We're talking about angular position, so the rate of change at which the angle change would be the angular velocity. And just like we did with regular velocities, it's delta theta over delta t. So it's change, the average value for a certain amount of time would be the change in angle over the certain amount of time, which has natural units of radians per second. We could, in some cases, we can write it as degrees per second or revolutions per second, but we'll see when we can use which units. And if we go to the instantaneous version of that, where it turns into a derivative, i.e. when delta t gets small enough, the instantaneous angular velocity is d theta dt. So here's an example where we have at t equals 1, it has theta 1. At t equals 2, it has theta 2. So the average of this would be the change in theta over the change in time. So let's do sort of a simple example. Let's just quickly say, let's say it changes by 2 radians over 5 seconds. So if it changes by 2 radians over 5 seconds, then we can find, the average omega here is going to be delta theta over delta t, the change in angle over the change in time. So it'll be 2/5, so it'll be 0.400 radians per second. Here's an example, right? We have standard speed for large records. Rotates at about 33 1/3 revolutions per minute. Okay, let's just convert that angular to angular velocity to radians per second. All right, so if it's revolutions per minute, we can convert it to radians per second. So let's start by writing the angular velocity in revolutions per minute. So I'll just approximate 33 1/3 is 33.33 revolutions per minute. So if I want to convert that, I need to convert the revolutions to radians, and I need to convert the minutes to seconds. So for the minutes, I'm going to say that 1 minute is 60 seconds. And for the revolutions, I'm going to say that 2 pi radians is equal to 1 revolution. And I set everything up perfectly, because then the minutes cancel the minutes, and the revolutions cancel the revolutions, and we end up with radians per second. When I plug all that in, I get 3.49 radians per second. All right, so that means it goes through a little more than one full. It goes through half. It goes a little more than pi radians per second. So what's next? Of course, we did position, we did angular position, we did angular velocity. So the next thing would be angular acceleration. We start with the average angular acceleration. It would be the change in angular velocity divided by the change in time, or in the instantaneous version, d omega dt, and of course it will have radians per second squared. So the example here is a ball on a string has an initial velocity of 12 radians per second. All right, so 12 radians per second, and over 10 seconds it changes to 36 radians per second. So its final angular velocity is 36 radians per second. So that means, and it says it happens over 10 seconds, right? So we can easily calculate the average angular acceleration. That's how fast, how its rotation speed is changing. So it's a delta omega over delta t. So it'll be 36 minus 12 radians per second divided by 10 seconds. And we get 2.4 radians per second squared. So important thing to note here. So I said it started at 12 radians per second and at 36 radians per second. So remember we said that positive means that it is rotating counterclockwise. So this thing is rotating counterclockwise. So CCW is just short for counterclockwise. They're both rotating counterclockwise. If I had said that as a separate example, let's say I said that the initial was minus 12 radians per second. So that means it was rotating clockwise. So this one here is clockwise, and final was the same. It was plus 36 radians per second. So it started, in this case, it started rotating clockwise because it's negative, and then at the end it's rotating counterclockwise. And let's say that this also happened over an amount of time of 10 seconds. So I can use this to calculate my angular acceleration. So it would be delta omega over delta t. And delta omega in this case is 48 radians per second. 48 radians per second. And delta t is 10, so we get 4.8 radians per second squared. Okay, so that's just examples of calculating angular acceleration. Now, we've sort of done the rotational versions of our three main quantities that we use for describing linear motion, right? Position, velocity, acceleration, angular position, angular velocity, angular acceleration. So it turns out you can show that these set of linear equations that we used, remember these near the beginning of the semester, you can basically replace all those values and you get the same angular equations. You get the same equations but the angular version of it. So here's an equation that gets us the angular velocity if you have the angular acceleration and the initial velocity. Here's the change in angular position if you know some of these values. So the relationship is the same as what we had before, and we can use that to solve similar problems. So let me just sort of do an example here, right? We have a disk that's spinning with an initial angular velocity of 20 degrees per second, and it's accelerating by 5 degrees per second squared. So we can use this to find the angular velocity after 4 seconds and the change in angular position after 4 seconds. I'm going to leave it in degrees. Since we're not using arc lengths here, S, we can just leave everything in degrees, and it sort of it makes it a little bit easier. So let's write down what we know real quick. So we know that the initial angular velocity is 20 degrees per second. I'll just write it in degrees per second. The accelerating angular acceleration is 5 degrees per second. And the amount of time that we're going to be looking at, or the time we're going to be looking at t equals 4 seconds. Now we can calculate these things. What is the angular velocity after 4 seconds? So we can use that equation number 1 here, right? We can just use omega is equal to omega naught plus alpha times t. So at 4 seconds, it would be 20 degrees per second plus angular acceleration of 5 degrees per second squared times the angular acceleration of 4 seconds. And we end up with 20 plus 20. We end up with 40 degrees per second. And you'll notice here that this second cancels out one of these seconds, and we end up with degrees per second in each case. For B, it says, what is the change in angular position after 4 seconds. So it's asking basically the change in angular position, right? Delta theta is just theta minus theta naught. So we can use equation 2 if we wanted to, right? So equation 2 says that, well, I'll just write as delta theta here. So equation 2 says that delta theta is equal to omega naught t plus 1/2 alpha t squared. I could also use, if I want to, I could also use equation 3. Since I know omega naught and omega, I could do either of them, right? You would get the same answer with either of them. 1/2 omega naught plus omega times t. Either of these will give you the same delta theta. You can try it out, and if you plug in the numbers for either of them, you get about 120 degrees, or sometimes I write it as 120 degrees. Right, so that's the change in angle for this sucker over the first 4 seconds. Another thing we can look at is if we start with this definition here of the arc length S, its relationship to the radius and subtending angle here. If I take the derivative of this, assuming that the radius stays constant, the derivative of S is just going to be some linear velocity, and the derivative of theta is omega. And so the linear velocity is related to the angular velocity by the radius. Another way of thinking about it is every point on this DVD is rotating with the same angular velocity. Let's say it's all 10 rotations per second or something. They're all rotating at the same speed, but this one out here, if the whole thing does one full rotation or 10 rotations per second, so they all make the same. They all take the same amount of time to go all the way around, but the one out here has to travel a further distance in the same amount of time as the one in here. So this one here, its linear speed, i.e. the direction in it's moving, at this moment, its linear speed is going to be much larger than here, because this here, in the same amount of time, has to travel a much smaller distance than the one out here, which has to travel all that. And so the linear velocity is going to be related to the angular velocity. Basically, it's directly related to how far it is from the center. And you can even, do a quick calculation to show the period. So remember, the period is how long, period t, that's the period, is how long it takes to do one full revolution. So what you can do is you can use that v is equal to delta x over t, or t is equal to delta x over v. Delta x is the circumference, 2 pi r, and v is related to omega by omega r. That gives us 2 pi over omega. So in other words, we have an expression for the period, how long it takes to do one full oscillation in terms of its angular velocity. So let's do a simple example here. We have 3 bugs on a disk, and the disk is rotating at 1 radian per second. Constant, it's rotating at a constant 1 radian per second. Okay, so we can calculate for each bug what its linear speed is. So for the red bug, its linear speed is going to be omega times its radius. So it's going to be 1 rad per second times its radius, which it's 15 centimeters out. Right, so rad is sort of not a real unit, so when we have centimeters here, that can go away, and we have 15 centimeters per second. Now if I were to do it for the blue one, v is equal to omega r, that's going to be equal to 1 rad per second times 10 centimeters, and we end up with 10 centimeters per second. And if I were to do it for the green one, it's omega times r again, and we end up with 5 centimeters per second. So the further out it is, the faster it has to move, because it has to travel a much further distance when it's further out. The next step is tangential and radial acceleration. So first, let's just look at something that's rotating at a constant speed. If it's rotating at a constant speed, that means the linear velocity of this particle is constant. It's changing direction all the time, but its speed is the same. So the only acceleration is the acceleration towards the center, right? That's the acceleration that we talked about before for uniform circular motion. So it's just an acceleration. In other words, we're going to call that the radial acceleration now. So it's just the acceleration towards the center that turns the particle, and the acceleration is always pointing radially inwards. Now, if it's rotating and speeding up or slowing down, that means that it's rotating faster and faster and faster, and that means there's a tangential acceleration. There's an acceleration in the direction of motion. And the radial acceleration we showed before, or the centripetal acceleration, is v squared over r, which, using your definition of omega, you can write the radial acceleration as omega squared r. The tangential acceleration, just take the derivative of s equals theta r twice, and you end up with this. This is the tangential acceleration, i.e. this acceleration here is depending on the angular acceleration, right? The faster the angular acceleration is accelerating, the faster this thing is accelerating. And of course, if it's pointing in the opposite direction, then it's slowing it down. If it's pointing in the same direction of rotation, then it's speeding it up. Here's a simple example of two bugs moving on a rotating table. And if I start them going here, it's going to show their angular speed. So let me go them a little bit faster. There you go. So they're both moving at a constant speed. All right, and I'm going to pause it real quick so we can see what's going on. So if you look here, constant angular speed, right? So they're both rotating at the same angular speed, but this one is moving a lot faster than this one. And the acceleration of this one has to be larger than this one. It's further out and it's moving faster. It requires more acceleration. Let's do an example. A rocket is moving in a circle with a radius of 3,600 kilometers. That's a pretty crazy radius. So 3,600 kilometers, and it's going crazy fast. And it's moving with a speed here of 30,000 kilometers an hour. Why not? And then it asks, what's the angular velocity of this thing? What are the radial and tangential accelerations? And how long does it take to do one revolution? So we can do all of this. So what is the angular velocity? So the angular velocity, okay, well first let's write down everything we know. So v is equal to 30,000 kilometers per hour. I think we can do everything if we leave it in kilometers and hours. The radius is 3,600 kilometers. And it's moving at a constant speed, so that means the tangential acceleration is 0. Okay? So it says, what is the angular velocity? So we can use the equation that v is equal to omega r. In other words, omega is equal to v over r. So we plug in, what's v? V is 30,000 kilometers per hour. That's very, very, very fast. And the radius is 3,600 kilometers. What do we get for omega? We get 8.33 radians per second. That's really fast. That's like 1.3, if you convert to revolutions, that's about 1.33 revolutions per second. So that thing is moving. B, it asks, what are the radial and tangential accelerations? Well, tangential we know. It's 0 because it's going at a constant speed. But the radial acceleration is the acceleration inwards that's turning it. And that's going to be v squared over r. Or we could use omega squared r. Either way, or we could use omega squared r. Either way, when you plug everything in, you get about 25,000 radians per second squared. So how long does it take to do one revolution? Well, to do one revolution, you do t is equal to 2 pi over omega. Right? So it'll be 2 pi over 8.33 radians per second. I guess this is radians. Right? And if you calculate that, we get that 2 times pi divided by 8.33, 0.754 seconds. Wow. So it goes all the way around that whole 3,600 kilometer radius circle every 0.75 seconds. It's a little bit insane. Okay, so one more problem I'd like to do. And it is this one here. We have a ball on a string, and it has a linear speed of 1 meter per second, and it has a radius of 2 meters, and its tangential acceleration is 0.5 radians per second squared. So that means whoever's spinning it is sort of speeding it up as time goes along. So let's write everything down. So v initial is 1 meter per second. The radius, which is going to be a constant, is 2 meters. The tangential acceleration, that means it's spinning around faster and faster and faster, is about 0.500 radians per second squared. So let's see what we can do here. What is the angular acceleration? So the angular acceleration alpha, we're going to use equation 3 here. Let's number these equations. All right, so we're going to use the equation that relates the angular acceleration to the tangential acceleration. So alpha is going to be equal to the tangential acceleration divided by the radius, which works out to about 0.250 radians per second squared. If we look at B, what is the initial angular speed? So at the very beginning, because it's accelerating, so its angular speed is going to be changing, but I can use equation 2, and I can get that its initial angular speed is going to be equal to its initial speed divided by r. And when I plug in my numbers, I get about 0.500 radians per second. And then next is, what is its angular speed after 2 seconds? So we can use the kinematics equations that we saw before, like this. I'm using omega I instead of omega naught, but when we plug it in, we get that after 2 seconds, it's now moving at 1 radian per second instead of its initial 0.5 radians per second. And then finally D, what is its linear speed after 2 seconds? So you go V equals omega R, right? And V equals omega R is, you plug in 1 radian per second, and you plug in 2 meters because that's the radius. So it is moving at 2 meters per second. That's how fast it's moving after 2 seconds.